Gravity waves. There we go. So if we put a 1 here, that will make the OR a 1, and it feeds back into B. And if we take this away, it stays in memory, right? So that's what we call a basic memory circuit. Now we have different types of flip-flops, something called an RS flip-flop, which is also known as an RS latch, a clocked flip-flop. Okay, select 2, okay, good. And a D-type and something called a JK flip-flop. So you'll notice little things here like Q and Q, bar Q, and these have their own little truth tables. And there's a little site called Falstad. I'll show you that. I think I have those in Moodle. That kind of gives you an idea on how those work. There we go. Oh, there's my notes, flip-flop notes. This decoder, NAND flip-flop, RS flip-flop. Well, this is a little site I discovered when I first started teaching. It's called Falstad. This is an RS flip-flop. So we have like a set and reset. So you'll notice here right now our bar Q is high. And we put a 1 here, or a 0 here actually. By clicking on it, it makes it low. And by doing that, it turned off Q and made Q high. And then to reset it, we take away a 1. So these are a little different in regards to setting with a 0 or setting with a 1. So we have an OR flip-flop and an AND flip-flop or NAND flip-flop. So we'll have a look at that. That is this guy here. So those are the different flip-flops. Sometimes they'll call them SR flip-flops for set and reset, or instead of reset, set. So here's our, what we call a NOR flip-flop. Here we're setting with a 1 and resetting with a 0. So they don't explain that very good, I don't think, in this particular example. But when you look at the truth table, where is it? That's the NOR. Yeah, so here we are with zeros in on our inputs. We're in the memory mode or no change, right? We set with a 1, and what we're setting high is Q, and bar Q will just be the opposite. So in this case, we're setting Q with a 1, and of course our reset is setting it back to a 0. And of course, prohibited here. The reason they say that is if we actually put 2 1s in there, this thing just kind of goes nuts and it completely flips and flops all the time. So that's the truth table for a NOR RS flip-flop. So we're setting with a 1. The NAND, so there's the difference, the demorganized equivalent. So basically you've got two NANDs in here and they're tied together like this. But in this case, they are setting with a 0. So they don't explain that well. We always have a 1 on these inputs. And we actually have to take away the voltage or set with a 0 in order to make Q go high, right? And we reset with a 0 to make Q go low. So that's the truth table. And of course, 0, 0 is considered prohibited in this case because the thing would just constantly flip back and forth. So you'd have to set up your circuit so you never had 2 zeros on each input. Okay, the RS latch. So this is what we would see as a switch bouncing. So if we had an AND here, or an AND I should say, and we have a constant voltage up here with our 5 volts. You can see my cursor. We need a 1, another 1 on this side right here in order to make that go out. But what happens if this switch is bouncing? Maybe it's a float switch. We could see this on the output, which could be nasty, right? We had a mag starter at the mill that was kind of experiencing this in regards to a photo eye. We didn't have a debounce timer in there, and the mag was banging itself to pieces. Basically, it was quite a big mag. I think it was a size 3 mag. So it's just something in the logic that we forgot to do. Once you put a debounce in there, we're good to go. But something called an RS latch could help eliminate this. Now, your drawing might be a little different. I think my drawing here doesn't work, and if we follow it through, I know there were some errors in the past. I believe this output here has to be a 0 in order for this to be true, because we're constantly supplying 5 volts here. In order to make this go off, we would have to make this a 1. So this is a NAND flip-flop. In order to make this NAND go set bar Q, we have to take away the switch. So when we make this a 1, that should turn this off. So they've got this backwards, I think. But either way, the idea here is once the switch makes or breaks, it's going to set, and we have to do a reset. So this could go all the way down here, break and bounce, but if it never hits reset, it's never going to switch on. So it's a bit of a bounceless switch. So it's either going to be on or off, basically on the way they described there. Now your drawing might be a little different. I know they've changed it. I think it was because of that issue. This should actually be a regular AND on the output in order for that to work the way they show it. But the idea here is this type of flip-flop, RS flip-flop, could be used as a bounceless switch, so it won't cause the output to go on and off all the time. A clocked flip-flop. So here we're having a clock input that's going to constantly go on and off in a pulse, and we'll see a timing diagram in a bit. Notice here we don't have a little 0, so it's not an inverted flip-flop. So in order for this to output Q high, we have to have a set at the same time the clock is high. So we'll see that in the clock condition. So here we are here. So the clock, and you got to think of this as something moving in time. And when I'll pull up the false diode, I think I got one in there. We'll see that in a bit. You can see that this is something moving in this direction, let's say. And it's like a timing diagram. And once again, the best way to look at these is take a piece of paper and just kind of slide it across your screen. And when the clock is high and the set is high, Q goes high, right? And we're not going to reset and make Q low unless our reset is high when the clock is high. So this is what they call a leading edge trigger. So we'll think of these as moving. They're moving across your screen, right? So, and then of course, when we go back down here again, we went back high again when our set was high, when our clock went high, but we didn't go back low again until our clock was high and our reset was high, and then back again. So like once again, if you put a piece of paper across there, it's a little easier to follow. So there's a truth table, right? We can't get a set until we have a 1 on the clock and a 1 on the set. And of course, we can't have a reset until we have 1 on the clock and 1 on the reset. Of course, another prohibited condition here, so something we'd have to avoid. The data type, basically set stores a 1, reset stores a 0. So depending on what you need to do. Their uses are the clock trigger memory allows computers to store bits for later use. Right, so that's going on in a smaller scale inside your PC and your phone, I guess, right? But this is once again indicating a leading edge trigger. So if our data comes in as a high, tells us to, when the clock goes high, it sets our Q high and it stores it until we need it, right? We can take it out, maybe reset it. And when our data goes low and our clock goes high, right, we switch it off. Now the JK flip-flop is very similar to the RS flip-flop, but the only small difference is we've got an inverter gate in the clock. And they don't explain that very good, but that little circle there indicates we have an inverter gate there. And because of that, we have now what we call a trailing edge trigger. So when we have zeros, when J equals is K, we are in memory mode, right? If J equals K equals 1, we're in toggle mode, and the output will just kind of flip and flop all the time. We'll get like a frequency divider. So they do mention the symbolized here as the trailing edge trigger. That's basically an inverter gate on the clock input. So once again, the only difference between this and the RS flip-flop is our trigger point, right? So now when our clock is going from high to low and our J is high, our Q goes high. And at the same time Q goes high, our bar Q goes low. So when the K is high and our trailing edge trigger hits, our Q goes low. And of course, once again, following that over with a piece of paper, you can see based on those rules, trailing edge trigger, those flipping back off and on again. You kind of explained it there. Something called a preset and a clear. And once again, those little circles indicate an inverter gate. So with a 0 here, we technically have a 1 on the clear point. Multivibrators. They're used to build more complex circuits like counters and shift registers. Shift registers we used at the mill for tracking boards and tracking what to do with those boards, if they needed to be trimmed or what type of grade they had on for sorting. And there's bit shift left, bit shift right type shift registers. Something called astable multivibrator, monostable multivibrators, and what else do we got there? Bistable, something called the 555 timer. And of course, we can look at counters and registers for counting things, decade counters, ripple counters, and that's what a lot of these JK flip-flops are used for. Okay, there's a one-shot multivibrator, so that's happens 1 per pulse. So the input signal triggers the off state into the conduction. This forces the multivibrator through 1 cycle of changes, and then returns to the off stage again. They mention here that T equals 1.1 times RC, so that they kind of throw that at you in the self-test. So just when you get there, don't forget about that. It's very similar to T equals RC for the time duration. In this case, they throw in the 1.1. Here they're showing this timing diagram for the set and reset for the bistable multivibrator. counters and registers. One of the things that are a little more interesting when you're looking at the flip-flops is the up counters. So here we have a binary ripple counter that will count to, I'm going to get this all in here. Basically just counts to 3, right? So can't write on that, that's weird. Okay, I know the last class I was writing on the screen, but I can go back maybe to the pictures. We'll get to that picture. That was this guy here. So there's your trigger, our trailing edge trigger, right? So if that will trigger our 1 count. The next pulse, the trailing edge, turns this one off, triggers our 2 count. Now you got to think of this as our 1's column and our 2's column. And then of course with both of them on, that's our 3 count, and they indicate that here. And of course, the next pulse, it resets itself, and it resets itself because when we get to the 4 count, our clear button clears it, right? So when we put a 0 or a 0 here, this will go 1 and clear it. And that's what happens in our truth table. Right, so we get our trigger pulse. As long as we have J set to 1, right, it will count to 1 here. The next pulse, trailing edge, counts to 2. Next pulse, 1 and 2 are on, which counts to 3. The next pulse, right, it resets. And then it starts over. So we only can count to 3 in this case. So they mentioned something called the modulus of the counter. So if we have two counters, clear that off. So if we had a JK, like they set up there, if there's 2 of them, if we just go 2 to the power of 2 in this case, gives us 4 minus 1, gives us a count of 3. And we'll see that coming up later again in regards to 4 flip-flops. So 2 to the power of 4 equals 16 minus 1. We should be able to count to 15 with 4 flip-flops. Once again, if you use your, think of binary counting. I know this is a little messy, but and this is the truth table here. It's probably hard for you to see, but they've got, maybe I can pull it up in the pictures. Oops. Okay, pictures. Yeah. That might work better. Yeah, so you'll notice here, if I can write on it, that kind of zoomed it in. Cool. This is our 0 count, 1, counting in binary, 2, oh, there it is on the side. I don't need to do it. It's all written on the side over here. So all 1s. Let's shrink this back a bit. There we go. So this is our least significant digit, A, 1, 2, 4, 8. So when they're all on, we can see it counts to 15. So, but our first pulse here, when the clock goes low, A pulses up, right? So we're, once again, our J is going to be 1. when our J goes 1 and our clock goes up, it outputs QA. At the same time QA goes 1 here, it's feeding a 1 into our inverter gate. Then on the next pulse, A goes low, or actually A goes low here, but B goes high. So we've counted to 2. So that means this will output a 1, and so on. Then the next pulse, this will both output 1s. And eventually, as it pulses through the clocks, you'll see 4 1s. But on the 16th pulse, it resets. So all flip-flops are what they call toggle mode. So they're constantly going on and off. Now, it's a little easier to see on the fall set site, so we'll probably go back there and have a look. Index here. That would be a 4-bit ripple counter. So you can see on the left or the right side of the screen here, it's just counting up to 15, and then it resets. It counts 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, reset. And that's all it's doing, sitting there clocking on and off with our inputs here, and eventually just resets. So not exactly the same as ours as far as the reset goes, but close as far as how the JKs are flipping back and forth. And you can see down on the bottom here our timing diagram. The next was a 4-bit. The next one is a little funky. It's an 8-bit counter. And I'll open up these links in Moodle too if you want to look at them. So this one's just going crazy. So how high can the 8-bit counter to? Or we've got 8 flip-flops. So 2 to the power of 8 minus 1. So 2 to the power of 8 is 256 minus 1. That will count up to 255, right, before it resets. So here, yeah, so that one, it's nice to see it in action, right? So it's hard to imagine what's going on here. But yeah, so this is our toggle mode. Eventually it'll get a clear and of course reset and start over. Something called a down counter. So you'll notice here with this JK flip-flops, we've got the bar, or I should say the QA, the QB, QC actually pulsing out. For the down counter, it's the bar. Oh, sorry, no, it is. No, the bar Q is feeding the clock. Where up here, the Q is feeding the clock. So it's just another way of doing it, but in this case, counting down rather than up. A decade counter. So basically, we get a 10 count. Including 0, like that would be a 1. When we get to 10, it resets. And when you follow it through, I'll bring up this picture too. Where's our decade counter? There we go. Once again, if we have a 0 on the clear, that would mean we'd have a 1 here, right? But when you look at this NAND down here, having a zero is down here. I can't write a 0 for some reason. There we go. Means this is a 1. Which means these are 1s, which means these are 0s. So we're not clearing, right? And as you follow it through, you'll notice when we get to the count of 9, right, or at the count of 10, so at the count of 9, we'd have a 1 here and a 1 here. We follow that through. That puts a 1 here. But we need another one here, right? So in order for that to clear, we need to have B on, which is the count of 10, right? If this is 1, 2, 4, 8, we need to have a 1 here. So at the count of 10, it will supply 2 ones to this. And when we have 2 ones here, that makes this a 0. When those are all zeros down below, that means these inverters turn to a 1. And it clears, and then it starts over again. So it's a little tricky to follow. I know that will come up in the self-test and asking you what would happen if we changed the wire from D to C or something like that. So you'll see that later on. So that's our decade counter, and at the stroke of 10 is when it clears, so we'll never see 10. Now, if we didn't have that there, it would count up to 15. Just a synchronous counter versus shift registered, different types of shift registers, series loading versus parallel loading, serial out versus parallel out. And these are just the little chip mechanisms, and they show you a pile of complicated circuits. But also trying to show you here, and once again, a piece of paper across the screen helps. If our data in up here is a 1 or a 0 in this case, we shift that data every trailing edge of clock. Right. So in this case, get up to this page, get to the description. This is a serial in, serial out shift register. So each time the clock goes from 1 to 0, the data input here will get shifted. So if it's 0, it will shift to 0 every time it goes. So if there's a 1, so if the data is 1, then a 1 clock pulse, it makes Q01. Then the next pulse, or at the same time, it makes D1, 1. The next pulse, it makes Q1, 1, which also makes D1. Now, if this goes 0, zeros will follow at the end. So basically, we had a data in pulse, right? And then eventually things just shift all the way to the left. So serial in, serial out. So it's tracking, in this case, maybe tracking a board. Where is it going? But it's a 4-bit serial shift. And it takes, 4 clock pulses to shift that data all the way over. Yeah, so as long as D stays 1, they're going to make all these outputs turn to a 1. And if data goes 0, then the zeros would shift over to the left. And notice once again, the little inverter gate makes it trailing edge trigger. Serial transfer between shift registers. So here they're shifting this whole portion here, the 101, from one shift register to the next, right? So after clock pulse 1, we shifted 101 over to the right 1 point. The next pulse, we shifted 101 over to this position. And the last clock pulse, we're complete. We shifted the 101 over. So basically storing that information, serial data transfer. And then they're just showing other variations of parallel in, parallel out shift registers. You have to follow them through, not really. Once again, what makes this a leading edge trigger? There's no inverted clock. I think the biggest thing to know here is how they work basically modulus of the flip-flop or the counter and such. multiplexer, so many inputs into one output. It's like a rotary selector switch. Now here we have a 2-input multiplexer. That'd be easier if I show that on here. Do I have a 2-input? Yeah, we do. So the input address that is determined to go out is or the data input, I should say, that's determined to output is determined by our input address. So right now, if we have a 0 here, it means we have a 0 here and a 0 here. By having a 0 here, that means this is a 1. And of course, if there's a 0 here, nothing outputs. And if there's a 0 here, nothing outputs. But if a 1 comes along from our data in, we get an output. Now we can follow it through with a input address of 1. That makes this a 1, which makes this a 1, which makes this a 0. So even if we have a 1 here, or a 1 I should say, nothing's happening. 0 here. So now with a 1 on the input address, A will be outputted. So it was a little tricky to follow. I just put the ones in and look at the rules and how they apply to each of the gates. And it takes a bit of practice. For the 4 input, basically S1 and S0 will determine what you output. So once again, many into 1. So notice here, the truth table on the right, if these are 0, which would mean these are 0 here, only 0 will output, or only this input, oops, there we go. If there's a 1 here, then that would satisfy A outputting, right? So 0 actually will be our Y output, indicated coming out this way. Once again, this is showing a binary count of 1, 2, 3. And of course, on the 1 count, when S is 0, then, or S is 1, I should say, that means this is going to supply a 1. We get the other 1 from here, and of course the 1 from our input, and we'll output B, or I1. And the same is for the next input. Now if we have S1 as high, we can follow it through. If this is a 1, that makes this a 1, makes this a 1, which makes that a 0. This is a 0. And we should be outputting 2. Yeah, so this is a 1. This will output 2, or C, I2. And of course, the last one, when we have both high, 1, 1, that makes this a 1, this a 1. And of course, when we input a 1 here, we would output I3. So counting in binary, once again, this is only 2 inputs. It makes sure you get all the combinations. And that's where it gets funky with a 16 input. It looks scary, but just think binary counting. Don't know if this will fit on my screen very good. We'll see what happens. I might be able to zoom it in. No, it's a big one. Let's see what happens. You might not be able to see it very good, but just once again, to keep this simple, think binary counting. Okay, we'll see what happens here. Let me zoom that in a little bit more. Maybe. Oh, I lost some of it there. So the trick is with this is what is our least significant digit? And the best way to try is looking at one, putting a 1 here, let's say. Well, let me put a 1 there. Nope, let's put a 1 here. Darn. Maybe I'm zoom mode here. Okay, why can't I draw on this one? Try that again. Edit, draw. Must be to crop it. Let's try that again. Reset it. It might be because I had it in zoom mode. There we go. So if we put a 1 up here, we follow that 1 all the way down to here. That makes this a 0. And follow it all down. You can figure out what your least significant digit is. So by putting a 1, I could try A, it might be a little easier to see. A 1 here. So 1 here, 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 and here. That makes this a 0. Yeah, so 0 gives us a all 1s. Here, so these would all be 1s by having 0s up here, which means if we have a 1 here, we will output the 0 data. So that one's easy to follow. Now, which will output the 1 data? So we'd have to have a 0 here. So that's telling me right away that A is not our least significant digit. So if we had a 0 here, we need at least a 1 from here, and we need 1s from the rest. Right, so I can't get my thing out of the way. Screen. Zoom back. Oh yeah, this is not working very good. Okay. Oh, now I'm using my finger to draw. Okay. Want that? Yeah, let's close this. Close that. Okay. It's just jumping around too much. Zoom. I gotta zoom this back a bit. I think we're at the minimum. No, I can't move it around. Yeah, so this is kind of tricky to follow, or hard to show you. But if you follow the dots here, maybe I'll go back to the module. It's not so jumpy. You just won't be able to see my 1s. But in order to follow this through, we need a 1 here. And all the rest have to be 1s to output a 1. So that makes D our least significant digit, because we can see that D comes down here. And then if that's the case, when we have all the 1s here, that's going to output our 15 at the bottom. So if we had, thinking of binary again, following that through, if our A is our, actually it wasn't A, wasn't our least in that case, it was like this. If we had a 1 on D and a 1 on B, that's going to be 5. So if we went back to here, 5 would output. And if we went a 1 here and a 1 here, that's 8 and 4. Oops, there we go. 12 would output. And it's a little tricky to follow. It's easier on in your book with your pencil probably than I'm trying to show you on the screen here. So just try and keep it simple. It's binary counting. I know there's a lot to follow through there, but what it's trying to say, we have many inputs into one. So depending on the combination of your A, B, C, and D will determine what data actually comes out. Oh, okay, what's next? So that's LTS4. So that's the big section. Now just the part that's the rest of it up here is just describing the integrated circuits. They're super reliable. Of course, when you look at a computer or even a PLC card, when you take them about, they're just full of little chips. And in the old days, we used tubes. Right? Tubes went away in the 50s. And of course, integrated circuits became the norm. High speed, less power consumed. They have digital type logic, and we'll see this again later on when we do process control. The digital logic type classification is either high or low, on or off, versus the linear or analog classification, where you can have a variable input, variable output, 0 to 20 or 0 to 10 or 4 to 20 milliamps. You might have heard of those terms if you're in industry. Combined digital linear. Small scale, fewer than 12 gates on the chip. Medium scale, and of course, very large scale, 10,000 or more. Now we're looking at billions now on processors and computers, which is crazy. Something called TTL logic. We had TTL cards at our mill for our scanners, and of course, different voltages and different speeds, and of course, different power consumptions. Now they are very susceptible to static, right? So static can really mess these things up. And you don't even have to touch it per se. Well, you only have to get close to it, and over time it will degrade it. CMOS, once again, very susceptible to static. Complementary metal oxide semiconductor. So we're back into semiconductor type materials again, where things are doped. CMOS chiplets are, when handling caution, they mentioned that static electricity from the human body can break down the dielectric, causing gate destruction. Now I have a little sheet. I don't know if it's in the middle, but just came from an Alan Bradley manual. But on a dry day in the wintertime, you can build up to 35,000 volts on your body just walking across a carpet. Right? And a CMOS chip is very susceptible. All it takes to degrade is 250 volts, 3,000 to destroy it. This looks familiar. That's a little diode with a transistor. There's our actual, and of course, showing the different dope materials. And there's our integrated chip package, DIP, they usually call them, dual inline package. And the little nipple here indicates usually, on the left of it, usually indicates a 0 pin and a silicon chip of some type. Of course, if we were in class, I'd be able to pass around some of these. And the different case styles, dual inline dip package with a flat pack, mini dip, and these things would just plug in to your computer or whatever. CMOS chips or BIOS chips in a computer, if you worked on computers, tend to just plug in. Identifying points, dipple, and usually pin one across from it. The gate type, it's all in the part number. A flat pack versus a metal can. What's interesting is I used to build computers, and the processors came with this ceramic leaded chip carrier, and these pins would stick out. Of course, people would bend them and it would damage them. And then the older style was just, if you got a picture of that, nope. The older style was just like Just still knobs sticking out the side. No, they don't have it here. I thought, yeah, I'll have to see if I can find a picture. But more kind of like this, I guess, but they don't stick out of the bottom. So they went the old style had the better design. They went to this style. Now they're back to the old style again. The shape's a little different, but they plug in the motherboard like the old days, basically. Now looking at floating points. So now we're looking at NAND gates and AND gates. So what they mean by a floating point is a point that isn't used. So either we have to tie it to a voltage or tie it together, right, for a NAND gate. Otherwise, the other gates won't do anything. So that's just a note to make, either tying it high or tying it to another input. And it's going to work. For an OR, we don't want to tie it to a high because that would turn the OR on. But it could be tied to ground or to another input. Right, to ground or to another input, where the NAND or the AND has to be tied high. Okay, that's another little quick section, and then we just get into the different testing probes. Connect and test digital logic circuits, logic probe versus a logic pulsar. Now a probe will detect ones and zeros in your circuit. A pulsar will inject ones and zeros in the circuit. Here's an example of a probe, a green LED, red LED. You can switch from TTL to CMOS, pulse memory select switch. Now, double check your module. I think there's an error. There was an error in mine, but just double check yours on that page. I'll just compare notes here. Yeah, so basically, when you look at here, the TTL logic gate recognizes a voltage equal or greater to 2 volts as an input 1. The voltages between 0 and 0.8 are considered a 0. Right, so with the selector switch on TTL, therefore, the green LED should light up, and hopefully your text says green. I know my text here says red, but it should say green. Lights up when there's a 0, and a red lights up when there's a voltage, right? So just double check your module, make sure you make that change. I think they've actually fixed that by now. Now for the CMOS, they also have it backwards in my module. In yours, hopefully it's fixed. The green lights up when the voltage is 30% of the supply voltage. So in other words, that's considered a 0. And the red LED should light up when the voltage is 70% of the supply voltage, which should indicate a 1. So that's the only change I was worried about there. The pulsar is, once again, is something that will test by putting zeros and ones into the pulse. And of course, the probe on the output will say, okay, did I get the pulse? So it's used for troubleshooting and testing digital circuits to see if they're doing what they're supposed to do. They mentioned scopes in here at the end. They say they're widely used for troubleshooting digital circuits, more so the digital scopes, I guess. Ironically, scopes have been taken out of the curriculum, but they still talk about them. We use them at the mill for scanners, but hardly you'll ever see them. Now more likely you'll see probably a power analyzer or something more specific for digital circuits for watching what happens. But you could use a scope to detect or see the waveform of the output. Okay, so that's all I wanted to cover this morning. I know it's a lot to kind of absorb at once, but I just wanted to give you a bit of an overview, just so that when you're going through those shift registers and maybe those binary counters, just try to keep it simple and think of it as something moving in time being caused by a pulse. And of course, the little circles are important in regards to whether they're leading edge triggers or trailing edge triggers. But I will open up a few more of these simulations. You can go check them out. and just to kind of see how things might work. One thing to be aware of, though, this site uses conventional current flow rather than electron flow. But either way, when it comes to electronics, that both theories technically work, right? All right. Where did my session go? There we go. There we go.